So today I will be talking about expected value in under 240 seconds. So first I want to give everyone a refresher of what probabilities are. So if I were to roll this die, what's the probability of getting a 1 on a fair 6-sided die? Well, the probability is 1 out of 6. And if I were to roll this die 60 times, how many times am I expected to see that 1? Well, I'll be expected to see that 1 10 out of the 60 times I roll the die. So intuitively, probabilities give you a measure of, in the long run, how frequently you will see a certain result. So now I propose a game. We're going to flip this coin. If it lands tails, I'm going to pay you $10. But if it lands heads, you're going to pay me $20. So now the question is, if we were to play this game, in the long run, what would be the average win or loss per game? So the expected value is meant to measure that amount that I just proposed of that one game. So this is the formula for the discrete case. And it looks kind of complicated, but don't worry, we're going to use the same exact example for the game to show you how to calculate. Okay, so over here I have written down the probability mass function in which I have shown the two cases. So as a refresher, I will pay you $10 if it lands tails, but if it lands heads, you gotta pay me $20. So over here as X, I have to know the amount of money that you can win or lose, and then these are the respective probabilities. So now over here, all you have to do to plug in this formula is you just plug in your X with your P of X, and then simplify, you have -5s. So this means that on average, in the long term, per game you play, you're going to lose approximately $5. So intuitively, you probably did not want to play that game with me, and I think it was quite obvious that I was not fair. So now let's talk about the concept of fairness. We consider a game to be fair if the expected value is equal to 0. So for the finite case, it's very easy to calculate expected values. But what about the infinite case? So suppose that I propose a new game. Flip a coin until you get heads. On the first turn, you'll get $2. On the second turn, you'll get $4. On the kth turn, you'll get 2 to the k dollars. So now my question is, what price would you pay for this game to be fair? So over here, I have constructed a probability mass function of the game I have just proposed. So you might be wondering, okay, how is the probability of getting $4 1 out of 4? Recall, you keep on flipping a coin until you get heads. So this represents getting tails and then heads. Similar concept over here, we have tails, tails, heads, and over here, you would get tails k-1 times, and then heads on the last time. So over here, I have plugged in the values into our formula. So over here, getting $2 is a 1.5 chance, and then getting $4, you have a 1.4 chance, getting 8, you have a 1.8 chance, and etc. So then what ends up happening is you keep on adding 1, 1, 1, 1, 1, and so the expected value is actually infinity. So again, our expected value is infinity, and theoretically, if you have infinity and you minus any arbitrary amount, you're still going to have infinity. So there's no acceptable fair price, and this is known as the St. Petersburg Paradox. So that's my short lesson with regards to expected value, and I hope you enjoyed it. Thanks for listening.